Hello friends, welcome back to the tetrahedron chemistry classes. So guys, as you can see in today's class, I am going to discuss electrophilic addition reaction. It is the simplest kind of the reactions which you have studied in your class 11th. But in today's class, we will see this reaction in little bit more detail, where I will also discuss the stereochemistry involved in this particular reaction. Basically, we generally use the reagent HBr, which will react with the alkene, right? So if you are new and the beginner here and want to learn organic chemistry right from the basics, so it is a very good opportunity for you to learn the things here in the pretty much detail, right? Say for example, you are having this CH2 double bond CH2, right? This is your alkene, and you know this alkene is having double bond in between the two carbon atoms. One bond is sigma and other one is the pi. And due to the presence of this pi bond, that means this available electron density, this alkene is basically nucleophilic in nature. Please remember, this alkene is nucleophilic in nature. So I am writing nucleophilic. Okay, it is nucleophilic in nature. So what is the meaning of that? If it is nucleophilic, that means it can attract towards the electrophile, right? So any electrophile can react with this one. You know, electrophiles are electron-loving species. From the basics of the organic chemistry, I think you know this thing, that the species which are either electron deficient or the positively charged, they actually react with the nucleophilic reagent, right? Say for example, I am treating this ethylene molecule with certain reagent like HBr. Okay, this is your HBr molecule, hydrogen bromide. A very famous reaction is this. So what will happen in that case? This pi electron will attack on this hydrogen and grab this hydrogen, and it will knock out bromine as a bromide ion from this particular position, right? So what you will get here, minus Br negative, and either of the carbon from this can get your hydrogen attached with it, right? Now you can see here what I did here. See, this carbon, this electron density grabs this hydrogen, and that hydrogen actually comes onto this right hand side carbon atom, making this as CH3, and this will remain as the CH2. Definitely this carbon is electron deficient now. As you know, this carbon is tetravalent in nature, and here its valency is 3 only, 2 with the hydrogen and third one with the with this bond which this carbon is forming with the carbon. So it is electron deficient. You know, the electron deficiency is always shown by the positive charge. So this is your reactive intermediate, which is known as the carbocation, right? So if this electron density attack on this hydrogen, and this hydrogen gets attached onto this particular left hand side carbon atom, so this will not make any difference. Let us say this time in the second instant, right? Say for example, in the first stage, in the first step, you can see here this hydrogen actually goes with this carbon. But what happens with when this hydrogen will go with this CH2? Let us take that case as well. So I can write here, this is CH3 again, and now this is CH2 and a positive over there, right? So you can see here, this carbocation and this carbocation both are same, both are equivalent. So it will not make any difference, right? Whether this hydrogen or the electrophile gets attached to the left hand side carbon or the right hand side carbon, it will not make any difference. Please remember. So basically here you can see this H positive is acting as the electrophile, right? And how actually we are getting this hydrogen as electrophile? When electron density is attacking on this one. So this and this both are same. And if you know the nature of the carbocation, so this carbocation is the primary carbocation. This is also the same, the primary carbocation, right? I hope you know, when this carbon is attached directly with one carbon only, then the nature of the carbon is the primary carbon. And when this primary carbon carries a positive charge, it is primary carbocation, right? And you will have this particular product. Now in the next step, what will happen? Say this is the step number 1. Right here, this is step number 1, and this is RDS, rate determining step. And in this rate determining step, you can see the electrofoil is basically this H positive as electrofoil. It is adding to this system. That's why the name of the reaction is the electrophilic addition reaction. Please remember, right? So what will happen in the next step, right? The Br negative, which was earlier present in the HBr molecule, now in the first step, it has knocked out in this way. But what will happen in the second step? It's a very quick step. This Br will go to this particular carbon atom and you will get this product. CH2, Br and CH3. Okay. So this is the only product, and this will also form the same product. There is no difference in that. And you have now converted this ethene into the ethyl bromide. Actually, it is a very important synthetic. This reaction is of very important synthetic application where you can form a saturated compound, especially your alkyl halide compounds from the alkene. Very important reaction, right? And you can see here one more aspect in that case. If you are having this double bond in between the two carbon atoms, this is basically symmetrical alkene. This alkene is the symmetrical alkene. So I am writing for this alkene is the as the symmetrical alkene, right? Symmetrical alkene. What is the meaning of the symmetrical alkene? Symmetrical alkene means on both the side, or you can say on either side of this double bond, the same number of the carbon atoms with same substitutions, if they are present like that only, then the alkene is the symmetrical alkene. You can see here, this is the double bond, left hand side the CH2 group, and right hand side also it is the CH2 group. So whenever your alkene is the symmetrical alkene, you will always get only one product in that case. Only one product. And in the synthetic organic chemistry, it is very important to get only one product, right? So whenever you have only one kind of the product in any reaction, then such reactions are very, very important because the yield of the desired product will be very, very high. But in case if you are getting more than one product, then of course the yield of the desired product would be lesser in that case. So whether this your ethylene molecule, or you can take this example as well. Say this is your CH3, this is CH, this is double bond CH-CH2. Again, you can focus here. What is happening here? This is the double bond, and on the right hand side you are having CH and CH3, and on the left hand side of the double bond you are also having CH and CH3. So left hand side group and the right hand side group is same. They are same actually, and this double bond is in the center. This is another example of the symmetrical alkene. This is also symmetrical alkene, right? And when you react this symmetrical alkene again, say with HBr, you are reacting this with HBr, again you will have this particular product, which would be your CH3, CH2, CHBr and CH3. So what had happened in that case? You see, this is the double bond, and I have attached this hydrogen with this carbon, right? The mechanism actually goes in that manner. This will come here actually, okay, and will liberate Br negative. And later, as you have seen in this top case, in the first case actually, so this Br will get attached with this electron deficient center. So here you can see it is attacking here. So this will become CH2 like that only. And that CH finally with positive charge will grab this Br negative. This will form CHBr. This is one product. And if you add, or if this carbon actually adds this this hydrogen to it on the right hand side, then what you will have? Then again you will have this kind of the product, which is your CH3, CH, Br, CH2, CH3. So what I did in the second case, I have attached this hydrogen onto this carbon atom. That's why it becomes CH2. And I gave this Br negative to this carbon. This will become CHBr. See, both these products are same. This is 2-bromobutane, the first one. Second one as well, you are 2-bromobutane. But if you are very beginner here learning organic chemistry, you have started this learning organic chemistry recently, then it is very important to you to learn the basics actually, right? If you do the numbering in that manner, this is wrong actually. Please wait. It's not like that. Okay, right? So what I can do? This is 1, this is 2, this is 3, this is 4. So what is the product actually? Product is 2-bromobutane, right? In that case, 1, 2, 3, 4. This is also what? I can write here 2-bromobutane. So both are same. Why we are getting only one product? Because it is the symmetrical alkene. So you will remember this point for your life actually, right? When you are, especially when you are an organic chemistry student, whenever your symmetrical alkene reacts with the halogen acids, whether it is HBr, HCl or the HI, it will always form the one product. Please remember, not only the halogen acids, any species which carries the positive and the negative charge. That means you can hydrolyze this alkene in the same manner, right? Or you can add H2SO4 in the same manner. Many reactions are there, but this reaction is very, very important. Now, the another very important special case, what will happen if my alkene is not symmetric? What will happen then? So here I have written the Markonikov's rule, and here you can see my alkene is like that: CH3, CH2, CH, double bond CH2, and you are reacting this system with the HBr. What product you will get? This is unsymmetrical alkene, students. Please remember, because you can see here from this double bond, and on this double bond, on the right hand side of this double bond, you are having only this CH2 group, and on the left hand side you are having CH, CH2, CH3. That means these two groups on either side of the carbon atoms are different. So it is unsymmetrical alkene. Please remember, it is unsymmetrical alkene. So I am writing unsymmetrical alkene, right? What will happen in that case? Whenever this HBr or say any electrophile reacts with this unsymmetrical alkene, you will have more than one product. Please remember. And when you have the more than one product, then definitely one product would be in the major amount and other one will be in the minor amount. And see, in 1870, Markonikov, Vladimir Markonikov, it's Russia. He was a Russian chemist actually, right? He studied this particular reaction, and he came to know that whenever you react this HBr-like substance like HI, HCl or H2SO4 or H2O with this alkene, especially when with the unsymmetrical alkene, then we will get the more than one product. And he said that, he gave the statement, during the addition of the halogen acids like HCl, HBr, HI, etc. to the unsymmetrical alkene, the hydrogen, which is generally electrophile in that case of the HX bond, gets attached to that carbon atom around the double bond which have higher number of the hydrogens. This is the idea basically, and why the Vladimir Markonikov gave this idea, we will see in a little while. So according to the Markonikov rule, see, this is the double bond, and left hand side of the double bond you are having only one hydrogen, and right hand side of the double bond you are having the two hydrogens. So according to the Markonikov, the hydrogen actually which is present in the HX, right, in halogen acids, this will add to this carbon atom because it carries higher number of the hydrogen atoms. This was the idea of Markonikov. So if we follow the idea of the Markonikov, then it is quite obvious. Say this is the pathway 1, this will attack onto this hydrogen, and this Br will be knocked out from here as Br negative. So what we end up then, this is your CH3, this is your CH2, and then you are having the CH and then CH3. And the center carbon is electron deficient, so we will put the positive here. And this is exactly what Marconi said. The H positive part, this is H part or the electrofoil of HBr or the HX will add to that carbon atom around the multiple bond which have higher number of hydrogen atom, and this is forming your secondary carbocation. So this carbocation is secondary in nature. 2 degree carbocation. And again, for the very beginners in organic chemistry, I am telling you, this carbon is the secondary carbon because it is attached with the 2 carbons directly, one on the left hand side and one on the right hand side. So the nature of this carbon is secondary and it is carrying a positive charge. That means it is cation made up of the carbon and of secondary nature. It is secondary carbocation, right? Say this is actually according to the Markonikov. But what if I will not follow the Markonikov rule? What will happen then? So you can see here, right? This is the pathway 2 I am taking, right? This is the pathway 2 and I am having my HBr, right? This is my HBr. So what I am doing in that case, I am attacking on this Br, right? And HBr, sorry, and getting this hydrogen and knocked out this BRS, Br negative from here. But this time I am giving this hydrogen to that carbon atom which is having the lesser number of the hydrogen atom, which is against the Markonikov. What will happen then? See, we can check here what will happen then. So the thing would go like that. CH3, CH2. This will become now CH2. This is single, this is CH2. Now you can see here what I did. I attach or I add this hydrogen to this carbon atom which is having the less number of hydrogen atom. Of course, it is against the Markonikov. Then I will get CH2 here, and this carbon is now electron deficient because it is trivalent now 2 and 3. So you will put positive over there. So what I will do, I will put the positive over there. Please remember, I am putting positive here. So that second species is also a carbocation. That second species is also a carbocation. And this carbocation is of primary in nature because this carbon is primary in nature as it is attached directly with this carbon only, right? Right? So this is primary in nature. So 2 carbocations I am forming. And from the basics of the organic chemistry, you should know your 3 degree carbocations are most stable, then your secondary, and then your primary. So I am taking only this particular case. I am not including your allyl carbocation or everything like that, your tropylamine. I am not actually considering those because we are not forming those type of the species here. I am only discussing the stability of the secondary, primary and tertiary nature, right? Necessary carbocation. So this is the most stable, followed by this secondary, and primary is the least stable. So now if you compare the stability of secondary carbocation and primary carbocation, so this one is the more stable one. I can write here, it is more stable. So what will happen if it is more stable, right? Its half-life would be very, very high. This would be less stable. Okay. So the half-life of this particular carbocation would be very, very high. That means most of the time this negatively charged Br will find this secondary carbocation because it is having the higher lifetime. Okay. So the more chances, statically what will happen actually, this Br negative will have more chance to attack on this secondary carbon atom. So what will happen in that case? This negatively charged species will add to this one, right? And you will have your product. And you can write your product in that manner. CH3, CH2, CHBr and CH3. And similarly, in the second case, what can happen? This Br negative can attack onto this carbon and you will have your next product, and this product would be CH3, CH2, CH2, CH2Br. Two alkyl halide you are forming here. Second one is the primary alkyl halide because it is forming from the primary carbocation. This is your secondary alkyl halide because we are forming from this alkyl halide from the secondary carbocation, right? And this is your basically the major product. This is the major product, right? Exactly, you can go through the literature whether it is 80% or 90%. I am saying that it is 80 to 90%, right? So remaining 10% would be this one. But in organic chemistry, it is not always the case that your major product actually will, your major product is 80 or 90%. It is not like that always. It depends on the type of the reaction. Sometimes if you have one product is 10% and other one is 20% and rest are the impurities, then 20% would be the major. Major means it is not mandated that your major would be in 80 or 90%. It could be any percentage, right? But it would be higher than the other isomers, right? So this is the mechanism. So whenever you are having the unsymmetrical alkene, you will always have more than one product, and these reactions are not very important. Why? When you have more than one products forming in the particular kind of the reaction, then the percentage yield of the desired product would be less, right? Now this is one thing. Now coming back to the stereochemistry of the reaction. So this reaction is this reaction which I have just written for this butene 1 and reacting this with the HBr. This reaction is regioselective reaction. This reaction is regioselective reaction. Please remember, especially for the beginners, this term is very important, regioselective reaction. So what are the regioselective reactions? If you haven't seen my earlier video, so I am giving you the link in the description box where I have explained the various kinds of the selectivity in the organic chemistry, regioselectivity, stereoselectivity, chemoselectivity. These things I have explained, right? So I am giving you the link in the description box. Interested candidates can go through the description box and learn the things from there. But here you can see what are the regioselective reactions, right? So I am explaining to you. See, focus here. You have formed two products in this particular reaction. One is major and other one is minor. And if you compare these two products, this is your 2-bromopropane. This one is the 2-bromopropane and first one is the 1-bromopropane. If you want to write the IUPAC name for this, so this is 1, this is 2, this is 3, this is 4. So the IUPAC name is 1-bromobutane because 4 carbons are there. Similarly, this is 1, this is 2, this is 3, this is 4. So this product is, I am writing here, 2-bromobutane. So this 1-bromobutane and 2-bromobutane, they are the positional isomers because the position of the Br is changing in the two products. And you know the positional isomers comes under the category of the structural isomers or the regioisomers. The name is different, structural and regio, but the meaning is same. Whether you call it as regioisomers or the structural isomers, both are same. In that case, these regio or the structural isomers are the positional isomers, right? And one is major and other one is minor. Such reactions are called the regioselective reaction. So let us give a definition. I am not writing the definition, but you can listen carefully. Whenever in any reaction we are forming more than one products, right? And out of these products formed, one is the major and rest are the minors. And all these products, if related as the structural isomers, then such reactions are called regioselective reactions, right? You can listen this, you can read this definition again and again from your textbook and apply the concept, then you will have a little better idea about these reactions. So this is the simplest case of the Markovnikov addition and the regioselectivity of the reaction. Let us move further. So guys, now you have been given this particular, now I am discussing some of the examples which will give you the more deep insight about this reaction. Okay. Say for example, you are reacting this HBr with this system. This is your alkene, right? And methyl substitution is here. So what kind of the product we will get? Now see, if you it will hardly take 30 seconds to make the products in that case. You know, this alkene is the unsymmetrical alkene. Why? Because CH3 is here and the bottom side nothing is there. So it will form more than one product. Two product will form. And it will take only 30 seconds to write the correct structure. What you can do here to write the structure? Add Br first to this one, add hydrogen to this one, and in the second stage, add Br to this carbon and hydrogen to this carbon. So you will add two types of the product. In that case, I am writing the product straightforward, just like that. So I am writing Br here. CH3 were already there. Of course, hydrogen will be here now. And one hidden hydrogen was already there. Please remember, one hydrogen is there actually. And what would be the second product in that case? Second product would be like that only. This CH3 is here, right? And now I am adding Br at this carbon. Hydrogen was already there, okay, and in that case you are giving one hydrogen. So what I did actually, see, in the first example I have added Br here and hydrogen here. I'll get this product. In the second case, I have added my Br here and H here. I'll get the second product. So you see, hardly 10 to 20 seconds actually will be needed to write the product. And now the thing is that which one would be the major product and which one would be the minor product. Okay. So let us decide which one would be the major and which one would be the minor based on the reaction mechanism. So how I can write the reaction mechanism? Please see here. This Br is attacking onto this particular hydrogen. Say this is pathway 1 and knocking out this Br as the Br negative from here. And in the first case, your hydrogen is getting attached to this carbon which carries the methyl. Please remember. Okay. So what will happen in that case? This is my 5-membered ring. Okay. CH3 is already there and I am attaching my hydrogen here onto this carbon atom, and one hydrogen was already there. If you count the valency of this carbon, it is trivalent. Center carbon is there, valency 1, valency 2, valency 3. That means it is electron deficient. You can put positive here. So this is your carbocation. This is your carbocation. And what is the nature of the carbocation? This carbon is connected with one carbon at the top and one carbon at the bottom. That means only with two carbon atoms this carbon is making connection. So it is secondary in nature. So this carbocation is 2 degree in nature. Now in the second instance, what we can do here? In the second case, say in the second case what I am doing, I am attaching my hydrogen to this bottom carbon. I am attaching to this bottom carbon. Okay. So I can write this separately. I can write this reaction. Okay. I am writing separately so that the beginners will have the better idea what actually I am doing here. So this was your species, double bond and CH3 and the hydrogen. And then you are having say plus of HBr, and this is attacking on this Br, knocking out this, attacking on this hydrogen and knocking out this Br as negatively charged species. and you are forming this particular product, or not product but the reactive intermediate, where these two hydrogens are here and this is your CH3. In the first case, I have added this hydrogen onto, you see, with this carbon here, but in the second instance, I am attaching or adding this hydrogen to this one. So now this is electron deficient, you can put positive over there. This is also a carbocation, but the nature of this carbocation is tertiary in nature. This is tertiary carbocation. You know, this is more stable. This tertiary carbocation is more stable and this is less stable. So more stable carbocation will have the more half-life. So most of the time your Br negative will find this particular carbocation and this will be your major product. So what will happen? Lastly, this Br will attack onto this carbon and you will get your product. And you can write your product in that manner. This is your 5-membered ring. This is your Br and this is your CH3, right? And 2 hydrogens are here. Okay. So this is your major product. So you can write here, you can see at the top, you can see CH3Br, this is your major. And in this particular case, what can happen? Br negatives can add to this system and you will have your product like that, CH3 and Br. This is minor and this is major. So out of these product which will form here, which one is the major and which one is the minor, you have decided based on the mechanism. So this is your major, I hope. Now again you can see here, I am not considering the stereochemistry. Please remember, I am not considering the stereochemistry of this reaction. I am only considering the regioselectivity. If I also take this stereochemistry in account, then one more feature I can add here. But right now I am not adding that feature. I am only discussing the regioselectivity. So this is basically, if you want to write the IUPAC nomenclature of this one, what would be the IUPAC nomenclature? 1, 2, 3, 4, 5. It is 1 bromo, fine, 2 methyl cyclopentane, and this one is what? 1, 2, 3, 4, 5. 1 bromo, 1 methyl cyclopentane, right? So this is 1 bromo, 2 methyl, this is 1 bromo, 1 methyl. Again the position of Br is changing. So these two are positional isomers, that means regioisomers. So the reaction is the regioselective reaction, right? This reaction is the regioselective reaction. Please remember, regioselective reactions can be of 3 types. Number 1, highly regioselective reaction. Highly regioselective reactions. Number 2, moderately regioselective reactions. Number 3, weakly regioselective reactions. When the difference in the percentage of the major and minor is quite high, then the reaction is highly regioselective. And if the difference in the percentage is little low, then it is the weakly regioselective reactions. I hope you are getting the things and understanding the reactions in the pretty much detail. Now you can have another example. What you can do here, this example is rather very, very important example. Okay. And what you can do, See, I am not actually doing this example. This example you can do by your own, by following the same guideline which I have explained you for the last reaction. So I am not doing this one, but moving further. Right, see, you are having this kind of thing. So what can happen when you have the substrate which is looking the unsymmetrical kind of the alkene, right? And what will happen if you add HBr to this particular system? What product you will get? This is something very, very important. And by solving this particular example, you will learn a very, very important concept here. And this concept generally you will find everywhere in the organic chemistry where you will form the carbocations. Right? Whenever you are forming the carbocations in the reaction, then you will meet this particular concept as well. This is something very, very important. Now I am going to discuss what is happening in that case, right? So this double bond, right? This double bond can attack onto this hydrogen and knock down this Br as Br negative. So you can write Br negative here. Now you are having the two chances. In the first case, you can add hydrogen to this one, which is according to the Marconi, right? And in the second step, you can add hydrogen to this system, which is against Marconi. Same thing you can do here actually, right? So here in that case, see, in the first case, where you are adding your hydrogen here in that case. See, first is according to the Marconi, where hydrogen is having like that, okay? More number of the hydrogen, because at this position you are having not any hydrogen. But here you are having the hydrogen and you are adding this hydrogen to this system. That means according to the Marconi, and that's why you are getting the major product. So same thing I'll apply here. So two kinds of the reactive intermediates will form in that case. So now I am straightforward writing two kinds of the reactive intermediate. One by adding hydrogen to this according to the Marconi. So I am writing Markoni. Markonikov's, according to the Markonikov's, right? So what will happen according to the Markonikov's? This is C, this is CH3, this is CH3, this is CH3 again, this is CH, single bond CH2, CH3, and a positive charge over there. So this carbocation is the 2 degree carbocation. So let us take different color. So I am writing 2 degree carbocation. 2 degree carbocation I am writing. Okay. And what another kind of carbocation you can get here? I am writing here. These are the 3 methyl groups. CH3, CH3 and CH3. Say this is CH2, this is against Marconi, and again this is CH2 positive, right? So this is carbocation, and the nature of this carbocation is what? Primary carbocation. Please remember, this is according to the Marconi, but this is not according to the Marconi. So you are having this and this. So what can happen in that case? A very, very important feature is here and actually, right? You can see this particular feature. What kind of the shifts are there? So for this one, right, I am doing for this one. So in that case, what I am doing the methyl shift. What I am doing? Methyl shift. So what is the meaning of the methyl shift? One of the methyl group along with the electron will move to this center. You know, for the formation of the bond, you need a pair of electron which is a covalent bond, and this methyl along with this electron pair will move to onto this carbon, and this will get attached here, and now this would be electron deficient, and you can put positive charge over there. Now let us write that structure with blue color again. Carbon, CH3, CH3, CH was already there, CH3 was already there, and due to the methyl shift, this carbon now carries this methyl here because this has shifted here. That's why I write like that. Now this is electron deficient. So this is your positive. Now focus, what is the nature of this carbocation? This carbocation is 3 degree in nature. 1, 2 and 3. This carbocation is tertiary. 3 degree carbocation. And here you can see this is primary carbocation. So is there any chance for this carbocation as well to convert into the more stable carbocation? Let us examine the things, whether this can happen or not. So what can happen in that case? Here hydride shift will take place. So I am writing hydride shift, and more precisely it is 1, 2 hydride shift, and this one is 1, 2 methyl shift. Why 1, 2? See, this is position 1, say this is position 1, this is position 2, so it is shifting from 1 to 2. Right? So again you can see here, this is 1, this is 2, hydrogen will shift from here to here, 1 to hydride shift. Okay, so what will happen in that case? Out of these two hydrogens, one will move on to this carbon atom. Okay, and you will have this thing, CH3, CH3, CH3 as well. This is CH, this is CH3 now, this is positive over there. How it had happened actually? One of the hydrogen I have moved from this position to this one, this will be now CH3, and this is CH, and this is again the carbocation, and this carbocation is of 2 degree nature, secondary carbocation. This is secondary carbocation, and you know this tertiary is more stable. So what will happen in that case? Your Br negative will add to this carbon, right? And when this will add to this carbon, you will have this product, CH3, C, CH3Br, CH, CH3 and CH3, right? You are getting this particular product. If you want to write the IUPAC name, what will happen? 1, 2, 3, 4. So it is 2 bromo, okay, dash 2, 3 dimethyl butane, dimethyl butane. This is one of the product, right? And here what can happen? This is Br negative will attack onto this carbon, and it will give you your product C with this CH3, CH3 and CH3. This is CHBr, this is CH3. Again, if you want to write the IUPAC nomenclature for this one, so you can number it carbon 1, carbon 2, carbon 3, carbon 4, right? So what would be the IUPAC nomenclature? 2, 2 dimethyl, 2, 2 dimethyl, 3 bromo butane. So again you can see your product, your this will be your major product. This will be your major product because it is coming from the tertiary carbocation. So you can write it as major product, and this one is the minor product. Okay, since you are forming the two regioisomers, one is major and other one is minor, reaction is a regioselective again. Regioselective. So what new thing you have learnt here, right? So you have learned the shift, 1 to methyl shift and 1 to hydride shifts. And please remember, these 1 to hydride shift and 1 to methyl shift will always be there in any reaction Whenever there is a possibility of converting less stable reactive intermediate to the more stable reactive intermediate, here you are converting your secondary carbocation to tertiary, right? You can see here secondary to tertiary by 1,2-methyl shift, and by 1,2-hydride shift you are converting your primary into the secondary one. So this will always happen. Okay, please remember. And this is your another example, and this example actually I have taken from the book which is Claydon, and this is quite important example. See, there is a very famous and very demanding organic chemistry textbook, little difficult one for the beginners actually, Claydon, Warren, Walther, Greaves, Organic Chemistry. It is from the Oxford publication. Very standard book, but you need to learn lots of organic chemistry earlier actually before going into this particular book. So this problem is actually I have taken from the Claydon. So what had happened? What will happen in that case? Again, a very, very important reaction. It is very easy to write the product, right? The same reaction, right? How I can write the product in that case? See, first you add hydrogen to this carbon and Br to this carbon. So what product you will have? What product you will have? Just like that, CH2, Br. This is product 1. And what is the second product? Add your Br to this carbon and hydrogen to this carbon. What will happen then? You will get this thing, CH2, Br, CH3. Now you have to decide which one would be the major and which one would be the minor one. Whether the reaction is regioselective or not. You have to decide these things. Very, very important things. So I am following the two pathways. First pathway, this is attacking on to this hydrogen, knocking out this Br negative from here, and say in the first instance you are forming this thing, 1, 2, 3, CH2, single bond, CH2, and put positive over there. This is the carbocation. What I did here, this hydrogen I have attached to this, right? And this will be electron deficient. And in the second case, what I can do? In the second case, I can add my hydrogen to this carbon, right? From the right hand side of this CH2, double bond CH2, right? So your second structure would look like this one, okay? And you will have CH, single bond, CH3, this is plus. This carbocation is what? This is 2 degree in nature. And this is 1 degree in nature. There is no question of any kind of the hydride of the methyl shift, because substrate or reactive intermediates are not like that which can shift hydrogen or methyl, right? So you are having these two species. But you can see here, this particular carbocation is highly stabilized because it is kind of a benzyl carbocation. It is highly stabilized due to resonance. I hope you know what is resonance. I can draw the resonance structure, few of the resonance structure. Say this electron pair has moved here. So what you will end up then you will have this thing, right? And this would become double. This is CH, this is CH3. And now this is electron deficient, you can put positive here. This is one of the resonance structure. I hope you know what is the resonance. If you are beginner here, again I am giving you the link in the description box for the resonance. learn what is the concept of the resonance, how we can understand the things. So this has moved from here to here, this will become double, this is now electron deficient, like that only. Similarly, you can move your electron, right? So this can come here. So what is the next possible structure for this? I can write double bond CH3, okay, this is double now, and this is like that, this is positive, and then this can come here as well, and you will have your another structure resonance stabilized. This is double bond, this is CH and CH3, this is electron deficient, and finally what will happen? This will come back to this position, right? And when this will come back to this position, then you will have your final structure, and that final structure would look like this and this, which is your CH and CH3. Positive is here. What is the difference between this structure and this structure? Only the position of the double bond is different. So this is highly stabilized, right? If it is very, very highly stabilized, what is the meaning of that? The Br negative of your HBr will attack onto this carbon, and you will have this product. Now I am writing in that manner, CH, CH3 and Br. Actually, study shows that reference is the Claydon, organic chemistry by Claydon. This is the only product form. This will not form any kind of the product because this is much more less stable than this one. So this will not at all form in the reaction, and you will have only one product. When you will have the only one product, there is no case of the regioselectivity. So according to the Claydon, this reaction is not a regioselective reaction. Please remember, okay? Now this is another problem from the Claydon, right? So again, what you can do, you can write the two products. So I am writing in that manner, Br, this is my one product, and my Br, this is my another product, right? So you can learn the things by your own. So now it is up to you how to draw the mechanism of these two, and you will decide whether the reaction is regioselective or not. If you get the answer, comment in the comment section, I'll reply. If you don't know the answer, then again comment in the comment section, I'll reply there what is the probable answer. Second thing, again you can see this, you are adding HCl to this system. So quite simple, benzene ring is there, no problem in that, okay? So in the first instance, what I am doing adding Br here, okay, and H here, and in the second case I am adding Br here, H here. Now again it is up to you to decide whether the reaction is regioselective or not, or only one will form. Again, this is a homework for you, and try to solve this particular problem and reply in the comment section if you get the answer. If you don't get the answer, then again you can reply, I'll answer there. And probably, so this again you can do by your own, very simple problem, okay? So product you can now very easily write. In first, Br here, in the second, Br here. These are the two products. You can draw the mechanism and the shift like that. And this is what my last reaction, okay? So this is basically again the problem from Claydon, but I haven't written. This is problem again the Claydon. This problem is again from the Claydon, and this is your actually starting material, right? And you are reacting with this HBr. So please remember, whenever you see these kind of the molecules, don't afraid, right? or don't be quite cautious ki what I will do, right? So see, what is the basic reaction? This double bond is here, this HBr is here, so this will react onto this system while the entire rest of the part of the molecule will be unaffected. This will not affected by this one. And this since this is the reaction which I am doing on this alkene system, there is no question of this reaction on this benzene ring. Avoid this reaction. So what can happen in that case, right? If you follow the Markovnikov, Markonikov's. What Markonikov says that around this double bond, your hydrogen will add to that carbon which have higher number of the hydrogen atoms. So here only one hydrogen is there, right? And here there is no hydrogen involved. So the hydrogen will add onto this system. How? Like that. Okay? It will knock out the Br negative. So what you will end up with this species. NH I am writing okay. So this is H, this is another H, and now this is your system, which is this one. Of course CF3 is here and Cl is here. Now this is carbocation, electron deficient in nature. When it is electron deficient in nature, what will happen? This Br can add here. So when this Br can add here, you can draw this structure again. My NH, and then this system H here. Sorry, I made a little mistake here. Earlier we are having hydrogen already. Okay, so this is hydrogen again, and this is where the benzene system not affected, CF3, Cl, and now you are having Br here. Now what you are doing here, you are hydrolyzing this is A, this is B, you are hydrolyzing it. Hydrolyzing it means you are reacting this with HOH, you know, H positive, OH negative, right? And this again you can see this reaction goes through via SN2 substitution, or rather say nucleophilic substitution reaction, right? You will decide whether it is SN1 or SN2. What will happen in that case? You see, this is where tertiary carbocation. What will happen? Now you have formed this particular alkyl halide, right? This is your alkyl halide, and this alkyl halide you can see here bromine is substituted on this particular position. So now in the second step, what you are doing, you are hydrolyzing this particular bromide ion. So this will undergo the hydrolysis, and bromine will be knocked out from here under the influence of this H2O, which is your polar protic solvent, right? This is polar protic solvent. And if you have followed my lecture earlier for SN1 and SN2 reaction, I already told you for SN1 reaction you need the tertiary kind of the alkyl halide more specifically, but here it is not tertiary, but it is say 4 degree in nature, right? Alkyl halide is like that, and polar protic solvent is also required. So this reaction goes via SN1 reaction, and Br will be knocked out from here, Br negative, and when you remove the Br negative from here, so you actually form this particular ion again, and that this carbocation, when it is formed and you are hydrolyzing it, that means your water gets attached to this. So what you will end up then, this is your NH, like that only, and OH2 with a positive charge, and This is your CF3 and this is Cl. And what will happen finally? So for better understanding, I can write this in that manner. My H and my H, okay, earlier it is having two lone pairs over there. See here, two lone pairs are there, one is used, so it is left with one only. And finally what will happen, this will be knocked out and that hydrogen will remove from here as H positive, and you will have your final product. Final product is your NH, okay, and here your OH having, and then your benzene system, right, and this is your CF3 and this is Cl. So this molecule is basically a tranquilizer. It is a tranquilizer. Okay, the medicine which are used for to tranquilize the say sometimes animals, right? Like see, if you want to catch a man-eater tiger or say any leopard, then you have to tranquilize it. So for this, lots of tranquilizers are used, and this is one of them. I'm not saying that this will be used for this purpose, but it is a this molecule comes into the class tranquilizer. So I think this much of examples about your electrophilic addition reactions, especially the addition of HBr to the alkene system, whether it is symmetric or unsymmetric, right? So you'll get the lots of the product. Okay, I hope you enjoyed the lecture. If you understood the things, please like the lecture, do share with your friends as well, and don't forget to subscribe my channel Tetrahedron Chemistry Classes. So